Hello, this is a video that I've wanted to do for quite some time. As our YouTube channel audience has grown, thank you so much. We see an increasing amount of comments and questions about, hey, I've got this meter, it's amazing, what's the problem, what's the big deal with it, it does this, and everything like that. I guess when people buy a product that they think is doing a good job for them, of course, it's in people's nature to want to promote it to help other people. So the intentions are good. But this video, I'd like to talk about the reality of consumer RF meters and the idea of the specifications that the manufacturer says and why they're often, unfortunately, not even close to reality. So let's dig into this. First of all, if you don't know who I am, I'm Bruce Hildesheim, and I'm one of the co-inventors, co-designers of the entire Safe and Sound RF meter line. And that includes the Safe and Sound Pro, Safe and Sound Classic, or the new Classic 2, and most recently now the Safe and Sound Micro, which has been in the works for many years, and it's just fantastic. Why did I get involved in this to begin with? What got me involved in this? And it really started as being unintentionally exposed to long-term microwave radiation. And I grew up in an engineering world, and when I was studying for my license for amateur radio years ago, we were told the same thing. We have many videos on this, that unless the RF around you is thermally heating up your tissue, there is no problem. In other words, the statement that non-ionizing radiation is not harmful to you biologically. Well, as we know, and if you're watching this, probably you're very well aware that we can now look at DNA, and we're gathering lots of data that is in fact showing that long-term exposure to especially multiple sources of microwave radiation over a long period of time causes problems. So I was an unsuspecting victim. I lived in an apartment building that I could see cell phone sector antennas. I'll maybe put up some pictures here. Just outside my kitchen window, and after 5 years, after actually 3 years, I started to notice a decline in my health. But I didn't think anything of it, because I was like, well, it's beyond. I'm below the safety thresholds. The safety code 6, and it was like, well, there's no concern. I mean, obviously, the safety standards are there for a reason. Plus, of course, I had a Wi-Fi router at my place. The home phone that I was using at the time was a DECT 6 cordless phone, so the base station's transmitting. Anyway, you people know all that stuff already. So what happened was I saw this, experienced this decline in my health, and then I started looking into this, and it's like, whoa, wait a sec, things are not exactly what they seem to be, or what we were told. So, having a background in electronics and RF, my first thought was, okay, I need to get some test equipment. So, I started looking around. Okay, what's something that I can afford to start measuring the power density of what's going on? And I saw there was lots and lots of manufacturers for different meters and things, and they made claims that this meter covers 100 megahertz to 10 gigahertz. Other meters were saying 200 megahertz to 8 gigahertz, and it's like, okay, but as we'll get into, what does that really mean, and how do they come across those specifications? How do they claim those specifications to be accurate? I quickly learned that manufacturers make all kinds of claims, and what we're talking about is their frequency range they might make a claim of, But what I was thinking in my mind was, well, what is the frequency response? And many people, perhaps you that are watching this right now, would conflate the two terms. Like, okay, frequency range, response, whatever. I'm looking at something that tells me that this meter goes from this particular one is 50 megahertz to 60 gigahertz. And it's like, okay, so frequency range, frequency response. But as I started digging, and it's like, okay, well, how are they backing this information up? Or this specification up? And I learned very quickly that really nobody, or at least only one manufacturer at the time, was actually doing real lab testing of their products. And at the time, I mean, I'm not afraid to say, I mean, it was Gigahertz Solutions, since then, obviously, 9CI, we test all kinds of meters. We have everything here, all different kinds of popular meters that are on the market. Here's another one, all kinds of stuff. So we're interested in finding out what is going on. And when we do a video that is just showing what the meter is doing, what it's capable, what it can't do, what we are talking about is actual testing related to the kind of testing standard that I first discovered with Gigahertz Solutions, and it made perfect sense to me. In the RF world, when you have a piece of equipment that's either transmitting or receiving RF, it is formally tested in a lab. And when I say a lab, it's not just a room somewhere in a clean building that turns this unit on and fires some RF on it. A lab for testing RF equipment is often what's called an anechoic chamber, and I'll maybe put up some pictures here. We spend a lot of time in anechoic chambers, and most recently reverberation chambers. And why you can't test an RF transmitter accurately or an RF detector receiver accurately unless you're in a very controlled environment. And when I say controlled, I mean that there can be no external influences to what's going on, but also within that environment, you have to control reflections. In the case of an anechoic chamber, as you see, the tiles on the walls are designed to absorb RF, and you don't want any reflections, because I don't know if you remember in your days of physics in grade school, in a ripple tank there's the thing called constructive and destructive interference. Waves, just like RF, they can cancel each other out. And when things are in phase, they can increase the amplitude, and if they're out of phase, they can cancel. So in a typical home environment, when you're walking around, there's going to be this constant change. So you can't accurately measure the performance of an RF meter unless you're testing it in a lab. Okay, so that's the first thing. Then it's like, okay, what test are you going to do? How do we test this? Well, when a manufacturer makes a claim, a specification that, here's one that claims 200 megahertz to 8 gigahertz. It's a very common frequency range. Why that range? Well, it represents a majority of the RF sources that could be a problem for you. Now, another future video will talk about 5G, but some of the meters that we've been looking at do include millimeter 5G bands, but up in the 60 gigahertz or even higher. But as an aside, just so you know, there are the 5G bands that are starting to become active right now are much lower frequency. And the one in particular you might have even heard, we'll do a video about this, but what was causing problems with airports and airlines refusing to land at certain airports with massive 5G rollout was because the radar frequencies that is used for the onboard altimeter on a commercial aircraft, or many aircraft, the radar frequencies we're very close to the 5G frequencies that are being rolled out in North America. Again, we'll do a video on that, but my understanding was that was around 4.3, 4.2 gigahertz, something like that. Anyway, that's not the point of this video. I'm just getting distracted by that. The point is that frequency is covered in a meter. So when we hold up a meter and say, okay, or when you see a meter that says 200 megahertz to 8 gigahertz, well, there are many 5G bands that are included in that. And what is coming in the future will be the millimeter wave stuff. So the point being, the manufacturer is making this claim, okay, 200 megahertz to 8 gigahertz, or 100 megahertz to 10 gigahertz. If you read the instruction manual or go to the manufacturer's specifications on their website, you'll see a frequency range or frequency response. And so automatically then you should start asking, okay, well, okay, great. So this meter has a frequency response or a frequency range of that from 200 megahertz to 8 gigahertz. Okay, so how accurate is it? And when I say the accuracy, I'm saying normally what's done with RF equipment is you have a graph that represents frequency on the x-axis and relative response on the y-axis. Okay, so in an ideal world, we would want to see basically a flat line, so that if you've got, let's say, 1,000 microwatts per meter, per square meter at 200 megahertz, the meter will show in a controlled environment. Okay, I'll give you that. In a controlled environment, the meter will show 1,000 microwatts per square meter. And then if you pick different frequencies in that range, it'll still show that. That's what people assume. Okay, the reality of RF equipment is far, far, far from that. Okay, the most expensive test equipment, some of the stuff from behind, when coupled with proper antennas with proper equipment, I mean this is tens and $50,000 of equipment. You can get receivers and detectors that are very accurate, but what we're talking about in this video is consumer, or in the case of Gigahertz Solutions, prosumer equipment in the hundreds to low thousands of dollars. And suddenly the lines in reality are not that flat. So what does that mean? Well, you can say that a meter has a frequency range of 200 megahertz to 8 gigahertz, that it'll measure something. In other words, if the meter picks up some sort of a signal at, let's say, 500 megahertz, it'll show something on the screen, or it'll show a reading. But that same power density at another frequency could be 10 or even 20 or even 100 times lower or higher, depending on the frequency. And for whatever reason, well, there are many reasons for that, but people don't seem to care about that, and I think it's largely because there's a misunderstanding between frequency range and frequency response, and it's very important. This is why I initially, when I got involved in this and I wanted to get tools to figure out what was going on, I looked for a manufacturer that actually did lab testing. So when they say that their meter has a frequency response, it includes a frequency range and it includes a response plot, okay, as I'm showing there. And when a manufacturer has a response plot of, let's say, plus and minus 10 dB, okay, that means that across its frequency range, claimed frequency range, the reading can be 10 times too high or 10 times too low. Now that sounds alarming. It's like, oh my gosh, well that's terrible. Well, the reality of consumer and prosumer RF meters is that to make something that's cost effective and in a small size that you can actually hold in your hand, okay, you're limited by antenna design, funding, the type of, well, physical space, but it's a question of cost. So you have to arrive at some sort of a compromise. Okay, so a really good RF meter that covers a very wide frequency range, if it's got a frequency response across its specified frequency range of, let's say, plus or minus 6 dB, then that's pretty good for the for the price of a meter that's that's in the $500 or $1,000 range. Now, this one from Gigahertz Solutions, this goes from 2.4 to 10 gigahertz. And if I remember correctly, we actually had this in the lab a couple of years ago, but I think it actually does very well with a plus and minus, I think 4.5 dB. And that's incredible considering the cost. Okay, so again, you might be freaking out. It's like, whoa, wait a sec, my meter could be 10 times wrong. Yeah, it could be, and even worse yet, especially meters that make claims that they cover frequency ranges from 10 megahertz to let's say 10 or 20 gigahertz, or even 60 gigahertz or something like that. Okay. You're expecting a relatively flat line from that across that entire frequency range. Sorry, that's just not going to happen. Now, they can make the specification of a frequency range if they have a dedicated RF section, an antenna section that's geared around the millimeter waves, and another one for the X band, and another one that covers up to 8 gigahertz, and another one for the lower VHF and UHF frequencies. So yeah, you could cover a lot of popular frequency bands, but if you actually did a response curve, it would be very bumpy, and in some cases you could have differences that your measurement error is going to be way more than hundreds of times off, if not even 1,000 times off. So again, I don't think people are aware of that, and so if you just go by specification and that in your home environment you're measuring something, well, a lot of the meters are going to be relatively effective at measuring in the popular Wi-Fi bands 2.4, 5.6, 5.8 gigahertz, 2.1 gigahertz cellular, LTE bands, 4G, 3G bands. They'll be effective there. But as we're evolving and as more RF transmitters are being pushed out into the world, different parts of the spectrum are being used. And again, if you want to actually measure, it gets into another terminology. We make a distinction between an RF detector and an RF meter. An RF detector is something like this. This thing on my wrist will send me a vibrate alert to me to tell me that, hey, I'm in a really high RF zone. It's detecting that something is there and it's alerting me to that. That's an RF detector. An RF meter is when there's something that showed, a reading is actually displayed on the screen. So that's a differentiation that we make, and we feel it feels important. But what we want to emphasize is that frequency range versus frequency response are not the same thing. Okay? So what we want to see, and what we've been doing, and the reason that I got involved and started working with another amazing engineer, David, which you've seen a few times on videos, is that we wanted to create something that is affordable as possible, but at the same time have it tested in a lab, so that when we publish a specification for our meters, and in the case of the Safe and Sound Pro 2 in the instruction manual I'll show you here, there is a frequency response plot that's there. And that was done in a lab. Actually, for many of our meters, we tested multiple labs, and in the case of the Safe and Sound Pro 2, we tested in 3 different labs in 2 different countries. We even tested in a lab in Germany, so that we could have reproducible results in multiple locations to confirm our testing standards. So what we're proposing is that if a manufacturer wants to make a meter to help people out, fantastic, beautiful, wonderful. What we would like to do is to invite manufacturers to a testing standard. there's a few companies now, including Gigahertz Solutions and Safe Living Technologies and 9CI, that have established a testing standard using an anechoic chamber. Okay, and we're inviting and would like to see manufacturers in the future do the same thing, so that when they make a claim that their meter covers a certain frequency range, that they can back it up with an actual response plot. Okay, and we invite the consumer, we invite you to look for this and to ask questions of your manufacturer. It's like, okay, hey, you've made that claim for frequency response or frequency range. What exactly do you mean? And when you say, there's many manufacturers that that make their frequency range specification and response, and they say, plus and minus 3 dB. It's like, okay, can you show me the lab test data and procedure at how you arrived at that? And you're not going to get that. And so we caution you to just be aware. Now again, there are so many effective meters. There are so many meters that do different things. They look fancy. They've got these beautiful screens, everything. Fine. But when we get questions or sometimes even criticism about claims we make about certain meters, the idea is not to harm any manufacturer or any malintent. The idea is to just help, if we can, make people and manufacturers aware that they need to be a little more specific with their specifications, and that it's okay to have a good meter that does all kinds of things that suits the person's need, that has, let's say, built-in things for mag fields and things like that, and make a claim. It's like, okay, we tested in the lab, and in fact, it has a plus or minus 12 dB response in these certain frequency ranges. Fine, that's fine. At least then people are aware. But we are taking this very seriously, because going forward, we believe that there's going to be an increased amount of people that are suffering health issues. And people that are already involved, that are in medicine, that are starting to look into this, want test equipment. And just like other things in medicine, equipment that's used in medicine has to it has to be approved to a certain standard, a testing standard. I mean, if you went to a hospital to get an x-ray, wouldn't you want to know that that x-ray machine had a certain attested response of what the power of x-rays it was emitting from that device? Of course you do. Not to mention, well, any medical device, you want to have it well documented and well tested. And our point is that as more and more people become electrosensitive and become ill from long-term exposure to RF radiation and microwave radiation, the kind of equipment that's being used to actually survey their environments and for you to find out what's going on, you want to have an idea of the actual power density. First, to prevent you from having harm, but also, and this is the big one, is to prevent you from overreacting to something that's not really that much of a concern. This is the problem right now, is that some meters are hypersensitive at some frequencies, and at the same time completely deaf, if you want to make the analogy to the acoustic world, completely deaf at some other frequencies. Okay, so this is really important. So again, we're just asking manufacturers to, hey, step up your game, and if you need to make some tweaks for your front-end antenna design, there are places and companies and people like us that you can reach out to for advice and input on how things can be improved. Okay, so this video was it was a lot longer than I expected, and maybe a little bit of a rant, but I hope this helps. And again, we really appreciate the growing audience that we're seeing, and we're going to strive to maintain and promote this level of integrity and testing standard going forward. And if you look back in our videos, especially in the last year, there are many videos where I'm standing showing something about what we're doing. Check out our videos about, you know, when we're in the anechoic chamber doing testing. And again, we've got some really exciting things coming up. The Safe and Sound Micro, fantastic. For an electrosensitive person like myself, it's fantastic because I don't have to be taking out some device and having people ask, hey, what are you doing? I just can feel it on my wrist that there's something going on and that I need to move. The other thing that I would like to say is that I'm really inspired and pleased that I've come across, as I mentioned, with engineers like David, but a growing number of engineers now that used to believe what they were told in engineering school, that non-ionizing radiation is perfectly safe. And there's a growing number of engineers that are, I don't like the term tinfoil hat, because that's the term that, you know, a lot of electrical engineers use for people like us that have problems or question the current safety standards. And trust me, we're not tinfoil hat people. We're just actually looking at real data and seeing what's going on and embracing the fact that we can now look at things biologically and DNA, for example. We can look at things at a level and a detail that we could not do back 10, 20, 30, 50 years ago when many of these RF safety standards were created. So, holy cow, this is an even longer rant. Thank you, and look forward to sharing more content with you. Bye.